Hello and welcome to Achieving Low Latency Streaming at Scale. I'm Mike Talvensarri, I'm VP of Product and UX at Wowza Media Systems, and this is Jamie Sherry, Senior Product Manager at Wowza. We've both been at Wowza for almost 5 years, right? Getting there.
Yep.
For those of you not familiar with Wowza, we do streaming. We have a complete portfolio of products from end to end for streaming. Wowza Streaming Engine is our flagship software. It's media server software. We also launched Wowza Streaming Cloud recently, which is an end-to-end live streaming service. We have Wowza GoCoder, which is a mobile SDK and free app for live streaming and encoding from iOS and Android. And Wowza Player we recently launched, which is an HTML5 player. What is latency? I'm going to start with some definitions here of latency and a bunch of other terms that are important to the conversation. So latency is the time interval between a stimulation and a response. Or from a more general point of view, it's the time delay between cause and effect of some change in the system. So in terms of streaming, it's the delay between initial capture and the viewer. I like to think of it as the delay between reality and what you see in your player or on your television. Other related terms, time to first frame. This is related to latency, but it is not latency. So this is the delay between when you click the play button on your player and when video appears. You could have zero latency, if that was even possible, when you click that button when the video appears. And that is unrelated to time to first frame. It could take 5 seconds for the first video to appear, but that's not latency. People will perceive that as a bad experience, and they'll even say your latency is terrible, but what they really mean is the click delay. The time to first frame is terrible. The broadcast delay. This is something that some people don't even realize is happening. There is a 5 to 7 second delay in everything you've been watching for your entire life. And this is an intentional delay so they can delete profanity, bloopers, or violence. So this is latency, but it's intentionally introduced into the system for broadcast. Quality, generally, the higher quality video you have, the higher the resolution is, the more data there is to send. And when there's more data to send, your latency goes up. Scale. Now, scale is how far away your people are, or your viewers are, and how many viewers there are, and how geographically dispersed they are as well. If you have more viewers and more data to send, or it's going farther, latency is generally going to increase. And we'll talk more about both of those later. Bandwidth is how much and people use bandwidth and throughput, which are my next two terms interchangeably, but bandwidth is how much traffic your infrastructure can ideally handle in a perfect world. That's how much you can handle. Throughput is how much is really delivering. So when you purchase your cable modem package and it says you're going to get 100 megs down, that's the bandwidth, but your throughput's probably going to be 75 megs, and you'll think you're getting ripped off. And then bitrate is how many bits of data are being processed over time. Why is there latency? So I mentioned a couple things, distance and scale, but really latency is introduced at every step in the system. This is a typical workflow diagram for satellite, and I put Wowza in the middle because we're Wowza, but this could be any media server software or a cloud-based service in the middle. But you have delay from the satellite. I don't know how many people have seen the Louis C.K. routine where he says, give it a minute, it's going to space. That's what this is doing. Space is introducing latency. It's pretty far to space. So there's going to be some latency there related to the speed of light, which you can't really change. And then you're going into an IRD and into the capture card. Both of those are going to introduce some latency, probably minuscule. Wowza Streaming Engine introduces a little bit of latency. And if I'm going direct out to the viewer from the media server software, I have some latency related to transmission, and that is related to distance, how far away they are from the server. If I'm going to a CDN, they will also introduce some latency as well, related to just sending the bits out to all the different edges in preparation for delivery. So pretty much every step of the way introduces some latency, and you really have to think about latency at every step when designing your system. And I'll show a demo of this later. The protocol used for delivery, ingest and delivery, also impacts latency. Some protocols are more latent than others. Why is latency a problem? I get this question all the time, especially with flash dying and people worry about RTMP, which is pretty good as far as latency, and HLS and Dash are perceived to be not as good as latency. But we get this question all the time at trade show booths and with customers. And I like to ask them, it's not a problem, but people think it is. People think they need really low latency streaming all the time, but they don't necessarily need it. So in designing your system, because if you want low latency, it's just going to cost more. You're going to have to buy more expensive devices. You're going to have more servers, higher quality, higher bandwidth. But you often don't need lower latency. A 30-second delay is not often a problem. So latency doesn't actually matter. So really think about, do I need low latency? Does my use case need low latency? If I'm streaming high school sports, does it really matter if grandma in California sees it 30 seconds delayed or not? Probably doesn't matter. HTTP streaming, which is the most popular format for streaming now, intentionally introduces latency for improved reliability. So Apple HLS and MPEG-Dash, both by default out of the box, require 3 chunks to be loaded. The chunks are 10 seconds. That gives you a huge buffer of time for network hiccups. And then, buffering has been greatly reduced over the years due to things like this. And so reliability is improved with some of these things. But this talk is about latency, and for some live streams, latency is critical. If you're doing real-time communication, it's critical. Anything over a second is painful. If you're doing online gaming, any sort of remote control of devices, gambling, auctions, latency is critical for certain use cases. So just really think about the use cases and whether latency is important for your use case. I want to define, we hear terms like low latency, ultra low latency, real time. What do we really mean when we talk about these things? So I'm going to start at the left. Common HTTP latencies for HLS and Dash. These are upwards of 45 seconds, 30 to 45 seconds, depending if you're going through a CDN. And this is really for one-way streams to large audiences. I got to have massive scale. People want to see it in HD or 4K. And so I can deal with latency there. I really want really good reliability. But that's the latency. Reduced latencies is kind of 5 to 20 seconds, 5 to 18 seconds. And this will be live streaming of news and sports and things and content for OTT providers. Low latency, 5 to 7 seconds is typical latency for HD cable TV. And so we call low latency anything faster than that. And this is for live streams, game streamings, esports. Sometimes you want to try to match that 5-second delay if you're streaming television content, so it matches up with what people are seeing if they're watching on TV. You want to be shouting goal at the same time as your neighbor if you're watching a sporting event. And then near real time is sub 1 second. So this would be for real-time communications, conferencing, any sort of telepresence, real-time device control. I'm controlling a PTZ camera. I want to hit the button and see it pan right immediately. So that's near real time. So that's some definitions. I'm going to go into a quick demo that will hopefully work. Never know what's going to happen. What happened to my mouse? Oh, I need to get out of this. There we go. Okay, so this is a demo of what different protocols look like. Oh, it's not going to load. Let's try one more time. Let's flip to the other one. There we go. Okay, this shows you that protocol does matter. So I've got a camera here, and I'm going to wave at it, and you're going to see this cascade across. So top left, the first two are going out remote on the network. So the first one on the left is WebRTC transcoded. This is going out to a cloud server. The second one, which we'll talk a little bit more later, is a low latency API preview we have in Wowza Streaming Cloud. One of these players didn't load. When you try to embed 8 players on a page, the browser doesn't really like it. The third one is RTMP tuned. So I'm streaming RTMP to a Flash player, but I've tuned it for lower latency. And that's probably around 3 to 5 seconds. The first two are around 3 seconds. RTMP is kind of standard RTMP. It's around 5 to 8 seconds. HLS tune didn't load. That would be about 10 seconds. And MPEG-Dash is probably 10 seconds. The bottom two are standard latencies for what you're going to see on HLS and MPEG-Dash. This is no tuning in the player, no tuning in the server. So I'll make another face, and we'll watch it cascade across. So this really shows you protocol does matter. So you have to think about this. And you can see the RTMP ones, those require a Flash player. Their latency is pretty good on those. And that's why people are so up in arms about the death of Flash. Everyone wants Flash to die. Flash is horrible for the browser and performance, but you got to have something to replace it with. So the first two, WebRTC and the Wowza Streaming Cloud Low Latency API Preview, are pretty good as far as latency.
The bottom.
But yeah, the bottom two, you can see it takes them 30 plus seconds to come through.
That's funny.
So that talks about protocol. The first tool I said are remote. The other ones are all local to this machine. Camera going into Wirecast, going to Wowza Streaming Engine, running on this box. So there's no network involved. All right, back to the demo, back to the slides. There we go. Okay, what factors impact latency? I've talked a little bit about some of these, but really it's quality and scale. We look at this as kind of a triangle. I can pick one of these things. I can't have low latency and large scale and high quality. You can get somewhere in the middle, have sort of low latency and sort of high quality and sort of large scale. But it's really a trade-off. As you increase quality of your stream, as you increase scale, either through audience size or distance, you're going to increase latency. So on the quality and scale side, you're really looking at resolution. Is the stream two-way? Am I running multi-threaded? What's the frame rate? Actually, on that demo, because I had so many streams running on one box through a network connection, I reduced it to 15 frames a second. And I was worried about the network here, so it's only a 700K stream. But I knew it was going to be a bunch of little players, so that's how I got lower latency by decreasing my quality, because I knew what my playback experience would be. If I want smoother playback, what's my chunk size and how much buffering do I have? On the tuned ones, the HLS one didn't load, but the RTMP tuned, that was setting a low latency setting in Wowza Streaming Engine and also reducing the buffer size on, that was actually JW Player to 0, as opposed to the RTMP one, which had a buffer of 3. So buffering really matters. But with the buffer of 0, you don't have any room for error, any sort of network hiccup, and you're going to see buffering in the player. So it's going to be a degraded playback experience for your audience. On the scale side, distance is one of the keys. You just are not going to go low latency from New Zealand to New York. It's not going to be as good as going from Pittsburgh to New York. Number of participants, number of viewers, both of those, burden your server, burden the pipes. Number of streams, how complex is your setup? Am I just going from a camera into a server and out to the viewer, or do I have a CDN in the middle? Do I have various encoders or other processing going on in the middle? And the network variability is huge. As you get more distance, you're probably going through more servers. You have more chance for network variability. And then am I going to diverse endpoints? I could be going to a desktop browser, a smart TV, a smartphone, a Roku device. Those are all going to add processing time. And you're probably going to see varying latency on all of those devices. Quality. I mentioned this before. Higher quality is higher resolution, is more data to send. So if your network conditions remain the same, if you have a higher quality stream, you're going to see lower latency. So if you're going to add higher quality, you got to beef up your network. Trade-offs. There's a way to mitigate latency. I can reduce buffer. I mentioned this before, but that makes your stream more vulnerable to network hiccups. But reducing buffer will improve latency, but will probably degrade reliability. I can reduce the frame rate. I mentioned this. For those streams, I made it 15 frames a second just because I knew I was going to have 8 streams going into one server. But 15 frames a second may be good enough. If you're doing slideware, I don't need 30 frames a second to show this slide. You could probably do it with 1 frame a second. But 15 frames a second is good for talking heads, but going to be terrible for any sort of live sports or action. And of course, I can improve my network, but that's going to be expensive. So I can pay for more infrastructure, I'll have more overhead and more cost, but that will help as well. On the scale side, I mentioned distance, complexity, and variability. As distance, number of streams, and viewers increase, your network's going to be more imperfect, have more variability, and have more degradation. Again, trade-offs. You can increase the buffer size. This is going to add latency, but increasing the buffer will have more reliability. Your stream will be more resilient with any sort of network hiccups. If I've got a 10-second buffer, then I can handle a pretty long network hiccup. If I've got a 1-second buffer, I can only handle a short network hiccup. TCP versus UDP. UDP is lighter weight, so it's generally lower latency, but there's no error checking, no monitoring. UDP will just drop frames on the floor, so that's a trade-off as well. There's some technologies like SRT and others that will help UDP be more TCP-like, but you still have no guarantee the data is going to be received. And then you can increase throughput again. You can always increase your network to achieve better scale and better latency. And now I'm going to hand it off to Jamie, who's going to talk kind of more about the history of latency through the ages and talk more about how to achieve it at scale.
Thanks, Mike. Hello, everyone. So where has latency been? So I bring up legacy technologies because these. How many people are familiar with Windows Media? Did they ever use Windows Media? Okay. So I've been doing this a long time, and I use Windows Media and Real and QuickTime were the choices back in the day, about 10, 15 years ago, right? And I bring these up because they were thinking about latency back then, and these are really well done technologies. They are no longer used, but they're great examples to rely on when we talk about the future of latency and other aspects of streaming. So when you talk about Windows Media, they had their own protocol called MMS, and they leveraged RTSP, which is a low latency streaming protocol designed specifically for media. And they use HTTP2, meaning as well. They used, both had an ability to use UDP and TCP. So they'd actually start on UDP and then fail over to TCP in general. You could set them up to do whatever you want, but that's how the default behavior was. And the general way that they would talk about reducing latency back then was to look at buffer management. So the encoder and the server and the player were kind of the pieces you had in a simplistic way for streaming back then. And the encoder buffer size could be reduced, the player buffer size could be reduced, and you could tweak stuff in the server too. The player, it's interesting, back then you had a desktop player, right? You had Windows Media player, and you didn't have Flash, you weren't in the browser, although Windows Media could be embedded in the browser. So you had a little bit of a limitation there, but eventually they allowed you to configure the buffer dynamically in the player, for example, when you leverage Silverlight or newer technologies from Microsoft back in the day. They would also talk about codec, like this low delay audio codec selection that you could use to try to reduce latency as well. It's not just about the buffer, it's not just about the network, it's about the data as well. So a high quality, a decent quality codec that is, low latency optimized would help as well. And then they have techniques that Flash imposes as well, others use as well, things called fast start and advanced fast start, which actually gave the ability to kind of speed up how you got the start delay down, which Mike talked about, as well as things like fast recovery, fast reconnect, and they actually implemented some forward error correction. And these are all techniques while you're streaming to try to keep up and not lose your quality or issues or have buffer issues when you were actually playing the content if you had network changes. So they would talk about 15 to 20 seconds latency by default, but they could get down on a good network to 2 to 3 seconds. Mike talked a lot about a good network. I'm going to keep emphasizing that too. A lot of this has to do with having a good network. If you have an unpredictable network like the internet, and you don't have ways to smartly navigate through the internet, then you're going to end up with some limitations. So the RTSP protocol, developed by Real Networks and a few others, Netscape of all people, was another one that was a really good protocol at the time. Real was another leader in the space. They're now gone. Relied on RTP and RTCP. RTSP is actually the transport not reliant on, or not responsible for the actual media delivery. And RTSP had an advantage of being able to use UDP and the ability to send frames one at a time in real time, which got the latency down to sub 1 second, down as low as potentially what I've got here, which is 125 milliseconds, which is actually pretty good. So, as well, now we move forward in time a little bit. We've got the real-time messaging protocol developed and open sourced by Adobe. This is the Flash streaming protocol. I'm sure you all know that. Still widely used. Will continue to be used on the publish side. The playback side, as you all know, is hitting a dead end, and again after the first dead end with Steve Jobs on iOS. It's now hitting a dead end in the desktop. But people have a lot of great success with this protocol. Again, a stateful protocol that has 1 to 3 seconds on average, and you can definitely get below 1 second. We've had people tell us they went in Amazon from Ireland to Vancouver in sub 2 seconds, which is impressive. And they're a particular customer that needed to use this for sports-related, time-based, like low latency sports betting types use cases. So Okay, and then we've jumped to HEP, as you all know, most popular format out there today, HLS, 30 plus seconds. iOS needs, on a 10-second chunk, they need 3 chunks, that's 30 seconds. So not low latency in any way, shape, or form. And then MPEG Dash comes along, and it is a little bit better. It's variable because it just depends and doesn't have these restrictions that Apple has on iOS devices. So, but those are all really too high for anyone who wants to use these in a low latency application. Okay, where are we going? So I'm sure you all heard of at least WebRTC. It's been around for a long time, actually, 7 or 8 plus years, maybe more. Designed for real-time audio and video and data over good to less reliable connections. RTC stands for real-time communication. So natural thing here is two-way chat conversations as an example for that. And obviously, if you're going to talk with somebody, you need it to be low latency or have low latency. You don't want to wait for somebody to hear what you said, and then they have to wait the same. So. Can use TCP or UDP. Again, we talked about network stuff before. A lot of these, we'll talk a little bit more about that later. There are advantages to using TCP and UDP and disadvantages and things like that. And my opinion is there's not a perfect world with either today, and that's why you'll see some of these other technologies show up in one of my next slides here. WebRTC actually uses multiple protocols under the hood that are all related to or based on RTP or TSP. So, and typical latency, 1 second or less, as low as 200 milliseconds or lower is what you're going to see there. WebSocket's another. This is something that is a two-way communication protocol that works in the browser. It works really well. It works with, if you've heard of MSE, which is what people are using to do HTML5 playback for audio and video, it works well with MSE as well. So it works on top of TCP, and it can be, it's not, I wouldn't say it's totally agnostic, but it can be leveraged with all sorts of streaming protocols and formats. So some examples here are RTMP and WebRTC, Haivision's SRT, and we have a protocol called Wowza, which looks very much like RTMP. All these things can be used with WebSocket in conjunction, and you can get as low as, again, about 200 milliseconds. Your mileage may vary, but that's the general number that we're putting out there. So HTTP, again, those other protocols, the challenges there are, let's go back real quick. So the challenge with some of these, as you may or may not have experienced personally, is if you're trying to replace Flash, for example, and you want to use WebRTC because it's got good latency, even if you're not doing two-way situations, people actually use RTMP successfully with two-way conversations and other two-way video delivery. But Flash does a lot of great things. So if you have what I call advanced features on top of your video, you're doing captions, you're doing encryption, you're doing all sorts of things, advertising or monetization and otherwise. You're going to run into trouble trying to use WebRTC to replace RTMP. So that's something you should all keep in mind if you don't know that or haven't experienced that. So what we see with these technologies is not only a lack of parity on functionality, being able to do what you want to do with your use cases or what you're trying to do with streaming. The other side of it is, while a lot of these have security, which is good, the scalability of these requires a lot different infrastructure and a lot more expensive infrastructure than HTTP. As we all know, HTTP is popular because of caching infrastructures that are already out there, like CDNs. You can just leverage those and use them for the delivery, but then there's the latency challenge. So techniques that people have been considering and are using and considering further to try to reduce HTTP. The natural thing people say is, okay, I have a 10-second chunk. Why don't I just reduce that to something much less than 10 seconds? Apple actually will tell you, I don't want to misquote them because they don't like that, but down to 2 seconds, I believe, and then Dash down to something much lower as well. And so you can reduce chunk size. But I don't personally feel like that's enough. I think, as Mike said, if you have a network degrade situation happening, you're going to end up with a user experience that's subpar. You're either going to simply miss data, which means the video is going to not, you won't see part of the video. But there's other considerations of quality degradation. And so you've got to make more changes than just doing chunk reduction. Along with chunk reduction, have to do keyframe or GOP adjustments as well. But some techniques that people have been talking about are to leverage CMAF. I don't know if you're familiar with that. It's common media, I forget what the A stands for, format. So this is an ability to try to merge the worlds of HLS and Dash a little closer. People are using that in combination with HTTP 1.1, what they call transfer coding, to basically create, I call it chunks of chunks. It's kind of a horrible quoted name, but you basically can reduce the chunks down to sub-chunks, and you can then start delivering faster before an actual full chunk is delivered to a player. So you can kind of speed things up there. You can also optimize parameters within the Dash spec. Some examples here are the availability, start time, min buffer time. Again, these come simply back to just reducing buffer time, reducing startup times. Again, which have trade-offs, right? If you're gonna do that and you're not gonna maintain a high enough buffer as you normally would, for example, Flash used to go up to 8 seconds by default. If you're not gonna do such a thing like that, then you run the risk again of issues with the playback if you don't have enough buffer. So the last part relates to decode. People don't talk a lot about it, it seems, but when you talk about impacts in the workflow for latency management, you have the encoding, you have the delivery, you have decoding as key parts. The decoding is another part of this, and people are trying techniques. There's a technology or a technique really called H.264 GDR that's part of the encoding enhancements that can be used to help with decode on the other side. So these are some of the things that people are trying to do with reducing HTTP, because people would love to just continue to use CDNs and use caching infrastructures if they can, but it is again a kind of an up and coming area, and people are still experimenting. A couple more here to talk about, just examples. By the way, there's numerous others that I didn't mention. We certainly could talk more about those. So Google has what they call QUIC, which is Quick UDP Internet Connections, is what it stands for. This is a technology that uses UDP with TCP fallback. It does focus on reliability and low latency, but has an angle of security built in, like some of the others do as well, like WebRTC and SRT do, for example. It basically tries to be like TCP without being TCP. So in sense of congestion control and connection and retries and round trip, it's trying to reduce all these things intelligently by stacking information and where it stores it, and trying to bring more along when it does different things in terms of requests for content. And it was built with HTTP2 in mind, so it's optimized for when an HTTP2 network is in use, but it does work on HTTP as well. The next one, SRT. So Haivision created a technology called SRT, Secure Reliable Transport. It is it's a transport protocol focused on reliability. It has security built in as well. So reliability first, low latency second, but both kind of go hand in hand. And so the idea here is that if you think about an ingest from a server or a camera or an encoder going into a server infrastructure, an origin infrastructure, and you have either an unpredictable network or a network that can really go downhill quick, this protocol will help maintain the connection, maintain a certain amount of quality and securely while you are experiencing that network change, and will allow you to continue to deliver and deliver with a decent amount of quality. So again, as it says here, things that it accounts for are packet loss, jitter, which is packets coming in out of order, fluctuating bandwidth, and the like. So we at Wowza, not to pitch our wares again too much, but we have been working on low latency as well. So we currently have what we call an API-only preview feature inside Wowza Streaming Cloud, which is our service model, our service offering. We are using our Wowza protocol, which again, it's briefly said, it's an RTMP-like protocol. We're combining that with WebSocket to deliver into an origin edge, a scaled-out architecture, and origin edge architecture. So what we're touting in this preview right now is sub 3 seconds, and what that really means right now is origin to player. Eventually, we'll add the encoder or camera into that as well. But for now, we're saying that's origin to player, and that's a globally distributed architecture as well, I should say. So it's meant to be highly scalable, highly resilient. I things like that. And again, it's using those technologies to deliver to the player. Okay, so reducing workflow component latency. So again, I talked a little bit about, or talked about these protocols, the things you can and can't do with them. I think the overarching thing is, depending on your use case, what you're trying to achieve, and how latency is part of that use case. There are different techniques you can use. There isn't one silver bullet here. You can choose one of many protocols or technologies to try to solve these things. They have trade-offs. They have positives and negatives. But you really need to think about it every step. As I said, it's not just about the network. It's not just about the buffer management, which I do have listed here. It's content creation too. It's the features you need. In the sense, if you need to do transcoding, for example, that's going to introduce latency. That can be minor, but it can be major too. If you're going to manipulate content in other ways with metadata or with encryption or anything else, usually these things are okay, but again, it just depends. And it all depends topology-wise where you're doing these things in relation to how you're then delivering it to the user, which I know doesn't sound easy, but that's the way this goes right now. So content creation, things like codecs, again, I mentioned the H.246 GDR stuff. There's bitrate and resolution. These all impact things. Streaming workflow and devices, so whatever devices you're hitting on whatever networks they are, Wi-Fi, 4G, all those things have network fluctuations. Public internet, if you're on private connections with enterprise or corporate stuff, it can be different or it can be better because you have more control there usually. But and the workflow, again, reflects on what you're trying to do with the content before you actually get it to the consumer. Buffer management, the encoder and the player specifically, also the server. Again, you can reduce these buffers in these areas to almost nothing. But again, you run into the risk of if you have a network fluctuation or degradation, that you may have a negative impact on the playback. Network considerations really boils down to two areas: how you optimize the delivery using the transport protocols that we talked about, and the protocols that might sit on top of that. HTTP versus RTMP versus RTSP, and these transports like QUIC or SRT. And then how you reach your audience. So as Mike said, again, size, location, all those things matter in terms of the latency. The front runners that people are trying really today are things like WebRTC and WebSocket. There are definitely a lot of offerings out there that have from the ground up written services and software that use these under the hood to do what they do. And there are a lot of them that are doing really good things. And these pieces you need to just make sure, again, when you're dealing with proprietary protocols or proprietariness, these are standards-based, but essentially when you're not dealing with HTTP, you need, on the playback side, you need to have, I call them aware clients. Basically, you can't just drop a video tag, HTML5 video tag in a browser and have it work. You need to actually write some code around that to make it possible to do this. And then the server scale-out infrastructure piece, if depending on what protocol you use, the scaling of that in either an origin edge, kind of mid-tier topology or otherwise requires a lot of servers and a lot of specifics to those protocols. CDNs are definitely investigating and trying things and doing things in these spaces. So they want to keep their caching infrastructure going. They want to leverage, support new use cases and leverage that to support them. So what I call tuned HTTP, which Mike demoed, which is to reduce chunk size and to reduce other aspects of the content, are what I would call a front runner today, but there are CDNs considering WebRTC. There are, again, other options out there that I'll talk about in a second that don't use HTTP, use other technologies. All right, it's kind of a sideways segue, but measuring latency. So, you saw the demo and you could count on your hand or whatever to see the latency. People often ask, how do you measure latency? There's a lot of research out there actually suggesting different ways to look at this. I think it's pretty interesting. It's definitely not an easy thing, especially at scale, to do. And as you probably know, latency is measured in milliseconds or seconds, although some actually use frames of video to actually measure that. And what we do a lot of is visual tests. We'll put a clock in the video, and then you can measure that against your system clock that you're playing the content back on. And as long as your system clock is synced with an NTP server, and I suppose as long as the other clock is as well, you should be able to tell how it's going. The challenge there is with drift on NTP. Especially on our laptops, I noticed that even going to Apple's time servers, it can drift pretty quickly, and in a varied range from milliseconds to seconds. I've actually had 3 seconds drift in a matter of 15 minutes. It's just, it's not always a reliable way to look at that. When you talk about traditional streaming protocols like RTMP and others, you can actually put markers in there and use timecode to actually measure that as well. So there's other techniques other than visual pieces that people are using. And some people are trying to put signatures in video. I read about an audio signature or some other piece like that. But the bottom line is they all come back to time codes, and you're measuring a delta in time. So you can get fancy as you want, but you can do a visual test and kind of get the same results. So. Okay, options for low latency at scale. So again, I touched on the 3 components at the top. I mean, it's an obvious answer to how you would go about this. You're either going to build it, or you're going to buy it, or you're going to have a mix of pieces that you might build and or buy. So, but again, when you build it, you need to focus on the major areas and that's kind of really dumbed down. But the encoder, the server, and the player are the key parts that you need to focus on. Again, you need to look at the network as well, and certainly there's a variety of things within those components you need to focus on, buffer and protocol and all those other things. So if you're going to buy, the 800-pound gorilla on the block is working on low latency. That's Akamai. So they're definitely looking at ways to solve these things. Some other examples, of course, there's us. We have this preview I mentioned about. So we have a low latency option going on right now in our service. But there are others on the market depending on what you're trying to do. Agora.io is an example. They're a low latency CDN. They focus a lot on two-way conversation use cases, but they have the ability to deliver in other ways as well for low latency situations. The folks from Phoenix P2P are here as well. There's a booth. They have a booth in the exhibit hall. So they have a service as well that's scalable low latency. So there are no shortage of people trying to solve these problems. And I do think it's early days, but I think that eventually you're going to see a flood of people trying to solve these problems. So and they will. That's all we got. So I guess at this point we can take questions. Sir?
You mentioned using the WebRTC. I guess you are using from an edge to the player. So I have 2 questions. First is if the network condition changes, who does the ADR, whether it's on the client or it's on the server? Second is how do you compare the scalability of using WebRTC server compared with traditional stateless HTTP server?
Sure.
So let's repeat the question. So
Yeah.
question about WebRTC and ABR, if there's network fluctuations, and then comparing traditional HTTP to WebRTC as far as scalability.
Yeah.
You want to take it?
Yeah, so the first question, ABR. So WebRTC inherently, at least in my opinion, doesn't have ABR design in it. It wasn't designed for that kind of case. But there are aspects of the specs, the standards, that let you, there's terms like renegotiation, and there is a term, an acronym that I'm going to mess up called RTCB, I think. So there are techniques that people are using within the standard to actually renegotiate the connection and kind of treat that like an ABR experience. So it is possible. I have to admit. So we run a preview on a WebRTC feature in our software product, and people are asking us about this all the time, and people are actually trying this. But measure of success, I'm not really sure. It's a way to try to support an ABR situation, but it may not end up being the right option at all. There might have to be some innovation that ultimately solves that problem. And scale on WebRTC. So, I mean, you have typically and again, in my opinion, WebRTC is going to require a custom server, a proprietary server versus a caching server, right? Caching servers are much cheaper. Now, the quantity of them is a question. We have actually not done performance benchmarks. We haven't completed them on our infrastructure, so it's hard to tell you that well, you need 10, for any given situation, you need 10 WebRTC servers, and, caching is something else. So it's really hard to say. Caching's cheaper, but I think you'll need more caching servers than you would the WebRTC, but it's going to depend on the topology, how far away things are. I mean, there's all sorts of variables that go into that. So can't really say how many servers or what's better or cheaper, but you can kind of base it initially off the fact that the caching would be cheaper. So.
For some of the new protocols like WebRTC, uses different ports. What kind of problems do you have with like enterprise firewalls where 1935 is fine, but now these whole new things might not be accepted?
It's a big problem.
Questions about ports and network firewalls with things like WebRTC that don't use traditional streaming ports.
It's a big problem, but it's a typical one of UDP versus TCP. The UDP port range stuff, the fact that it's ranges is a problem in itself. The fact that it's custom ports, not 80, not 1935, is a problem as well. So the bigger problem, and we've seen with UDP technologies in general, is we recommend a wide range of ports to be opened. Amazon doesn't like that. For example, if you're going to run in the cloud, they'll take that whole range and knock it down to something much smaller. And so ranges alone are a problem, and that makes it hard to say on a secure network what you want to do there. So that's a drawback for sure.
The ports do for the WebRTC, are you going to run the Turn Stun server on the Wowza?
We do some limited stuff in turn, but we don't do anything with stun right now. So yeah, it's an external piece you have to pull in. Yep.
There's another one over here.
Do you have any solution for the encoder buffer size so that it should be a trade-off between the latency and also the network quality for the service?
Yeah, the question's about network buffer size on the encoder side. Okay.
I don't know if you do. I don't have a suggestion.
Usually you have to play around with it.
Yeah, you
My
kinda-
experience is set it really high and really low and play around with it and see what works.
The first
and
mile.
let your stream run for a while, because it may work fine for that first 2 minutes and then start buffering. So it really depends on other conditions as to what will work.
The first mile is really sensitive anyway for a lot of these technologies, especially Flash and RTMP. And so of all the things you could reduce, I would stay conservative on that personally, unless you know you're on a network that's reliable and got a lot of throughput. So, yeah. Sir?
How can you handle complex claims with WebRTC? I mean by that is you close that contracts for languages, people audio tracks, and support things like that, and mention it.
Questions about more complicated streams with WebRTC with captions and multiple audio and video tracks.
I personally haven't found an answer for this today. The challenge with WebRTC is if you were to run I suppose you could rely on the WebRTC data channel aspect and pipe stuff through there, but there isn't a guarantee on synchronization at all with, yeah.
And you'd
Yeah.
have to have a custom player built to suck the
Right.
captions or the other tracks out of the data channel to display.
Yeah, in a vague sense, I could imagine some sort of sidecar approach where you're actually, but then you've got a timecode issue, right? You ultimately have a problem where you can't map it back, and a WebSocket data channel would not solve that either, so because it's out of band, right? So it's a great question. If anyone has an answer, I'd love to hear, but I haven't personally seen an answer to it yet.
And that's one of the problems with WebRTC and WebSockets that Jamie alluded to, is they're just not as feature-rich as RTMP and Flash were. They're still kind of nascent technologies, and people have solved the basic streaming. If I want to do ABR or captions, multiple tracks, it's just not there yet.
Yeah, I'll reiterate. I just think people should beware. People look at it as a replacement for Flash, and they say that okay, the delivery looks great, and then they want to add all these other things, and there's a bunch of things you just can't do. So
One here.
we'll keep looking at it though, and maybe I could contact you or get your info. We could talk about it further. Yeah.
I have a question. In my business, I see DVR as a big, use case, and also for cost situation that I have the same kind of stream pipeline for live and bulk. But what you present here, I can just assume wouldn't work for that. This is exclusive to live, right?
Correct.
So do you see that merging in your roadmap or in the general ecosystem?
So the question's about live versus VOD with these new streaming formats.
But in the sense of use of DVR, right?
And DVR, yeah.
Yeah,
I mean,
yeah.
same screen, same asphalt.
Right, right. I don't know if I have a good answer. I don't see a lot of these technologies being used with a DVR experience right away. The challenge is, obviously, it's recording, right? You're recording for DVR and then going back and playing that content when people rewind and pause and all that, right? You're not playing from the live point, or the live stream. So my opinion would be they're leaning towards trying to optimize HTTP technologies like HLS or Dash, and that's how you get live plus DVR. So that's kind of my gut feeling for now.
Yeah, and with VOD, there's not really the concept of latency with VOD because you're playing from a file, but I think your question could be translated as I want to use the same player and the same transport and be able to seamlessly switch
Right.
between live and VOD.
Yeah.
So that's a difficult problem.
In the streaming part, because the CM model solution that is exclusively for live.
Yep.
And then you have to fork that out and store it on disk as a separate solution.
Right.
Yep.
And they are different format, or they are different
Yeah.
quirks, you know.
So we can take, with Wowza Streaming Engine, you can take WebRTC in and then record it, correct?
Yeah.
And then use that via, make sure I'm not speaking out of turn. Record it and then use that to stream back out, but you're still going to have the player and player issue.
And you wouldn't, in my opinion, you wouldn't necessarily want to do live a certain way with a different protocol. Even if, so let's say you had two technologies, one for live, one for DVR, that both work in MSC and HTML5 in the browser, right? You wouldn't want to necessarily layer those two on top or whatever, or flip between them when people rewind versus watch from the live point. MSC is going to puke. It just would not handle that well, in my opinion at least. So, I mean, someday maybe. Maybe it'd be nice if you could interchange those, but.
With the player we're using for Wowza Streaming Cloud, Wowza Player actually does the preview version, and it'll eventually be in all the versions, does WebSockets delivery, and it will handle VOD. Wowza Streaming Cloud as a service doesn't have VOD yet, but we're going to add that. So you would be able to use the same player at that point, but it would probably be different transport in the same player. Yeah. So that's something we're thinking about, at least from the playback side, but it's going to be different transport.
So for the WebSockets and getting that to play video, is there a lot of SDKs that allow you to take those kind of raw packets and then turn it back into video for the player? I never heard of that.
No. That's kind of an up-and-coming
Yeah,
thing.
question about WebSockets and building a player. Sorry,
No, I keep forgetting.
I'm the repeater.
Repeat the question. It's pretty new. There are people doing it, but for example, with our preview, just to go back to that as a reference point, we require our player today. Someday we will have to change that. We can't, I think, completely rely on our player. We'll have to introduce an SDK or a library, to broaden that support. I think others. It'll be interesting to see if other players in the market.
Well,
like JW,
there's at least one other one doing WebSockets. I'm drawing a blank on the name right now, but we ran across it.
Yeah, I don't
If you
know.
talk to us afterwards, I'm pretty sure there was a
Yeah.
couple other players at least looking at WebSockets. But yeah, you'd have to write custom code right now to pull out the WebSocket information. More questions? All right. If you have any more questions, feel free to come up and talk to us or get our card. We can correspond with you via email. And thanks for coming.
Yeah, appreciate you coming. Thank you.